All right. Yes, it's being recorded. All right. So for McCohen's class, the whole homework 3 was about functions, just an introduction to functions from Rn to Rm. And then he had some categorizations of like what a scalar field is, what a vector field is, what a linear function is, and how that can be represented by a matrix multiplication. You talked about level sets and defined continuity of function at a point. And then you had some topology, where you defined open ball, interior point, boundary point, open sets, closed sets, closure of a set, and this idea of boundedness. Okay. For Dr. K's class, they had a homework which involved the simplices, finding their volumes, maybe an application of cross product, and a problem involving Gram-Schmidt procedure. Okay, so we're dealing with functions defined on some domain, some subset of, say, Rn into Rm. So that's the general study of this class, or the calculus of such functions, really. So this is you think of this as the number of tells you how many inputs you have for your function. Or if you think of Rn as a vector space, it gives you the dimension of that vector space. And this gives you the number of outputs. And if you have specific questions from the homework, go ahead and raise them. I know you turned in homework 3 yesterday, I believe, so for Dr. M's class, so we can go over that. Okay, so so here's an example. D is a set of a subset of Rn. So D is a subset. So it's some region in the Euclidean space Rn, and here we use D because domain. So this function might not be defined for all points in Rn. So we use the letter D to indicate the subset of Rn for which the function is defined. So here's an example. So this is a function whose domain is what dimensional space? We have 3 inputs. Treat like a single input, which is a vector in R3. So this would be R3. And how many outputs do we have? How many coordinates do we have for the output vector? That's right. So we have a number here and a number here. So a vector with 2 coordinates is a vector from R2. All right. So what is the domain of this function? That's right. So you can take any point in R3 and plug it into these 2 coordinate functions, right? And it's always defined. So the domain is just all of R3. Okay. As opposed to, like, if you have another function from R3 to R2, Okay. So here we would write that this is a function with some domain, which is a subset of R3 because we have 3 inputs, into some point in R2. Sorry, R2. But how do you? What's the domain of this function? How do we determine? Well, it's just the common domain. So you can look at the domain of each individual coordinate, right? Like for which values of x is this defined? And then the intersection of those two, the separate domains for each coordinate, would be the common domain for the function, right? Because for the output vector to be defined, each coordinate has to be defined. So you might worry about denominators because you cannot divide by 0. It's being recorded, great. So looking at the first coordinate, what can you say? Well, you know that you have to exclude the origin in the domain, because for this to be defined, this cannot be 0. Okay, so if you look just at the first coordinate, the domain is all of space, but you have to exclude the origin. But what if you look at the second coordinate? So you have to worry about square roots, possibly logs in these problems, right? So since we're dealing with R to, Rn, we're dealing with real numbers. So we know that for real numbers, we can only take square roots of non-negative values. So this has to be at least 0. Okay. So if you look at the boundary of this, that's an equation of a plane. Okay. So that's hard to draw, but you can imagine a plane going through the origin. It's an origin through the origin. So you can imagine that you have some plane through the origin. It's very hard for me to draw. Okay, and you want everything, if you like, above that plane, so that this expression is not negative. All right. What else do we have? That's right. So let's see. Maybe I should have done this in let's say some subset of R2. Okay, so first of all, what do you call a function that has its domain a subset of Rn, and what comes out is a real number? The output is just one number, right? Say R1. What do you call such functions? It has a name. So you think of this as an example of this would be, it's not injective. That's not the correct conception here. It's not necessarily linear either. Just in general, if you have a function from Rn to R, so that you think of this as f assigns a number, because R is just the number line. The output is just a number to each point, or not to each point in D, where D is a point in Rn, right? So think of an example, let's say let's say I say the word weather map, right? So for each point on the map, I assign a number, which is temperature. That's not a level set yet either. So it's just a categorization of a function where for each point in Rn you assign a number that's called a scalar field. That's all I was going after. So let me just say it, scalar field. For each point in space we assign a number. So an example might be for each point in the plane, let this be 1 over the square root of x1 plus x2. Right, so you see that for each point in the plane, this is the output is a number given by this rule. Well, not for each point in the plane, right, but some subset. That subset of the plane is called the domain of the function. So what would be the domain of our function? Let's call it D. Yes, so two considerations, the square roots, we're dealing with real numbers, so we know that whatever you're taking the square root of, it has to be at least 0. Okay, but of course, we also see that that square root is in the denominator. So we have to have that x1 plus x2 is not equal to 0. So, yeah, so taking those together, we see that we just need to have that x1 plus x2 strictly greater than 0 to satisfy both conditions. Yeah, strictly positive, strictly greater than 0. So in set notation, we would say the domain D is the set of all points, and I write vectors this way, so all points in R2 such that x1 plus x2 is greater than 0. Graphically, you can say that, okay, this is x1, consider the boundary of this inequality, namely x1 plus x2 is 0. And we all recognize this as a line with a negative slope. Okay. And then we're looking for all the places where the expression x1 plus x2 evaluates to a positive quantity. So if you choose a test point like 1, 1, then, oh crap, sorry about that. Okay, slip of the mouse or something. Okay, like the point 1, 1, that would satisfy the inequality. x1 plus x2 is greater than 0. So it's everything above that line. Okay. Why did you set it equal to 0? Oh, so yeah, so when I graph an inequality, so imagine I graph x1 minus x1 squared minus x2 is less than 0. So that's like another example. Okay, so how do you graph such an inequality? So what you do is you consider the boundary of that inequality, the boundary of, so the graph of this is a region of R2. So I would graph the consider the boundary. So that that's when x1 squared minus x2 is equal to 0. So I want an equation because I know how to graph equations. So I would see that this is x2 is equal to x1 squared, so that's a parabola. And then I decide, whether this region is like above the parabola or below the parabola. So here it's where x2 is greater than the parabola where x2 equals x1 squared. So I would shade above the parabola to graphically model my region. Okay. So it's just a standard procedure when graphing a inequality. You consider the boundary first, and to decide which region to shade, if you will. Got it. Okay. So I know that I haven't defined it, but we know you've done homework problems where you're asked to say whether this domain, this set, so back to this domain, whether that's open or closed, bounded. So what do you think? So first of all, what can somebody? You can use your mic, by the way. Can somebody tell me what an interior point is? Oh, well, let me change that. Yeah, well, you can now speak up, I guess. 1 second. One more person. There you go. So what's an interior point of a set? Yes. So somebody want a point inside the boundary. Oh, so first of all, yeah, I would have to define what a boundary is and what it means to be inside the boundary. I know what you're saying, and you're right. Yes, Adia.
Wait, so I mean, I guess this is from the definition that I know of
Uh-huh.
that suppose there's a point inside the set and you were to draw a positive radius around that point. So if the boundary of that point is the subset of the set, then it is considered an interior point.
Yeah, so first of all, there's the idea of open ball, right? Centered at some point A, say, with radius R. So we consider it, what did you use to denote ball? That doesn't matter, but it's the set of all points in whatever space you're in, such that the distance between those points and the center is less than the radius. So that's open ball. So we think of it as we have a center, we have a radius, and the open ball is this all points that are within distance R of point A. So in one dimensions, that's an interval. So in R, you have a point, a number, and then you have a radius and A minus R, A plus R. So that's the radius. And all points on the line within the distance of A, that's R, that's going to be just an open interval. In 2 dimensions, such an open ball is an open disk, right? Call that an open disk. And in higher dimension, we just kind of generalize and we call it an open ball, right? In R3, instead of a disk, let me erase that. You would get an open ball. So A is the center and the radius of the sphere is R, but that would be an open ball. And so in higher dimensions, we just call these, like, as general, you call it open balls. Okay. But the idea is that if your point is on the interior of some region D, I can't use your name. So somebody said, it fits inside the boundary, yeah, but more precisely, there's some radius or some open ball such that it's completely contained in D. Right? All right. So so just to remind you, it's an interior point is one that's contained inside the region, but more precisely, there's an open ball containing it that's completely contained in the region.
And
And
we
yes,
can draw that ball as small as we need to
yes.
for it to be
So
contained in the region.
that exactly. So the idea is that even if you get close to like the boundary, right, you can still choose a ball small enough so that it's completely contained in the region. So you still have interior points when you get close to the boundary. So what is the boundary point then?
It's pretty much like the same definition, but it must contain points that are not in the set and also in the set.
Yeah, that's right. So for interior point, there's this important notion of that there exists. So there's at least, there's a small enough ball. Okay. It's completely contained in your region. But the boundary point of a region is one where so notice that here there's at least one ball, right? But here we have every ball, open ball, centered at the point. Contains points in D and outside, not in D, right? So outside D, so to speak. So that would be just like what you think, it's on the boundary, because I don't care how small or large I make the ball, there's a part of that ball which intersects D, and there's also a part which is outside of D, right? So the ball intersecting the complement of D is non-empty. So it makes sense. You're on the boundary if you have 1 foot in one country and a foot in the other country or state, whatever, right? Okay. All right. So using these notions, they defined an open set. All right. So what is an open set? Let's use A. An open set was one where every point of the set is an interior point. So the set completely consists of interior points.
So basically no boundary points.
Yeah, Yeah, so you couldn't, an open set would not contain boundary points. That's right. Because by definition, like a boundary point is not an interior point, right? Since for a boundary point, every open ball, part of that open ball is outside of the set. So there's no way that there's an open ball that's completely contained in your set. That's right. So that's a good one. Like if your set contains a boundary point, then it cannot be open. Okay. And then how do we define closed set? So B is closed if and only if what is true?
Like all the points are boundary points or something like that.
No. Closed set could have
Interior
contain
point.
interior points, but yes. So if so, B is closed if and only if all boundary points
Like a subset of the region.
are contained in the set in the region. Yeah. Okay. So you probably heard this joke from your professor, even though haven't seen the lectures, but I can imagine the joke was made that a set is not like a door, because a door is either closed or open, right? But a set can be both closed and open, neither, right? Or one or the other. So what's an example of a set which is both closed and open?
The universals.
Yeah. So an example. The universal set, or if you'd like, Rn, let's say R2 is an example, is both closed and open. So in particular, if the domain of a function is all of Rn, so if the function is defined for all possible inputs, then that domain is both closed and open. And this is because obviously, let's say if we just take the example of R2, since the region, the D is all of R2, every point is a interior point, right? Every ball, at each point, every ball around that point, centered at that point, is completely contained in R2. So it's definitely open. Every point is an interior point. And does the plane R2, does it contain all its boundary points? Right. Well, there are no boundary points. There's no boundary. This isn't, R2 is unbounded, right? It's not contained in a finite region. So by kind of default, since there are no boundary points, the set contains all its boundary points because there are none. Vacuously true. All right. So I'm going to read somebody's question here. If you are given an equation of a region, okay, so an equation that defines a region or an inequality that defines a region, how can you tell whether it's closed and bounded? Right, so let's look at some examples. So consider the region D, which is all points in the plane such that y is greater or equal to x squared. So graphically, I see that the boundary is just the parabola y equals x squared. And we would part of the region is where y equals x squared, right? Because of we want y is less than or equal to x squared, meaning that we would include that boundary in our region. And then where y is greater than x squared is just above the parabola. Okay. So what is, as we were saying, the boundary is the parabola y equals x squared. So does our region contain the boundary, all its boundary points? Yeah, right. As opposed to like if you had a different region, call it C. Where y is strictly greater than x squared, then we see that we would, if you draw the boundary, we would use a dashed line, typically, dash curve, to indicate that the boundary is not included. Here we used a solid line or curve to indicate graphically that we are including the boundary points in our set. Okay, so yeah, the boundary is the parabola, so we write the boundary of this region is the set of all points such that y equals x squared. And we see that that is contained in the region itself. So we say that D is closed. It contains all its boundary points. Okay, is it open? Remember, a set can be both closed and open, but here no, because even though we have interior points, right, we have open balls here that contained in our region, but because boundary points by definition cannot be interior points, okay, D is not open. Okay. So then, is this region bounded? So, of course, bounded means that your domain, so it's a bounded region. Oops, not rain region. R. If you recall, formally we say that if R is contained in a ball of a finite radius, so it's contained in a finite volume region, then it's bounded. So here we're talking about domains or sets. So here we're talking. So for a function, you can ask whether the domain of the function is bounded or not. But you can also ask whether the function, so the outputs, right, the values of the function are bounded or not. So that's a very good point. So let me give you an example. So, oh, by the way, here D is not bounded. Obviously, this parabola goes on forever. So this region, right, it cannot be contained in some finite ball. So like you choose a point. I don't care how large you want to make the ball. You're always going to have stuff that's outside of it. So it's the red region is unbounded. but I'll try to answer your question on yet here. So let's look at an example. So here, so this is going to be a scalar field. Yeah, okay, that's good enough. All right. There you go. So essentially, I could have made this more general and just said we have a scalar field on Rn, and this is defined by 1 over the square root of 1 minus the magnitude of x squared, right? So more generally. All right, so what is the domain of this function? I guess let's work with the general case, and we can model it by drawing this case. So the domain here, domain of f, or D if you will, we notice that we have to choose points so that the denominator is not 0 and at the same time it's positive, right? Or I'm sorry, not that, at the same time. It can't be 0 because the denominator can't be 0, and because of the square root, we have to have that this is greater than 0. So if you'd like, this would be all x's in n space whose magnitude is less than 1. X is all real numbers. No, so no, not a, yeah. So here we would have the domain being an open ball of radius 1, right? Because the domain is just all points in space or the plane or whatever dimension you're working with, where the magnitude or the distance to the origin, if you like, is less than 1. Okay, so the domain was open. Every point in this unit ball has its own open ball, which is completely contained inside. So D is definitely open. The D does not contain its boundary. That's right, because of the denominator, right? If we had magnitude of x equals 1, then we would have in the denominator 1 minus magnitude of x is 0. We can't divide by 0. Now the boundary of D is exactly all points on the unit sphere. It's all points where that are exactly distance 1 away from the origin. But D does not contain its boundary points. So D is not closed. So notice here we're talking about the domain of the function, right? And so if I ask, is the domain bounded? Let's say yes. It's a finite volume or area. Okay, but that's different than if somebody asked you, is the function, are the values of the function bounded? Is the function itself bounded on its domain? No. And why not? So that's a different question. So this was all about the domain of the function, including the bounded question. But then that's different than asking whether f itself bounded or closed or whatever. Because then you're asking about questions about the codomain or the range of the function. So they're talking about the values of the function. And so if you look at the function on its domain, like what's the function at the origin? It's equal to 1, right? Because you get 1 over square root of 1 minus the magnitude of 0 squared. So you get 1 over 1. Okay. But what happens as x approaches the origin? You pick points. You pick x's which are approaching the sphere where magnitude of x equals 1. Of course, the denominator is going to approach 0. So the answer to what happens is the magnitude of x goes to 1, I guess from below, is that the function goes off to infinity. Right? Because you get 1, a finite number, divided by something which approaches 0. So the value of the function blows up. Okay, so is the function bounded? No, right? The values of the function, the range of the function, if you use the correct terminology, is not contained, right, in a finite volume. So no, the function is not bounded. So you have to, as Adyat, you were thinking, you had to make a distinction between whether the domain is bounded. Here it was, and whether the values of the function is bounded. So the values of the function are bounded.
Could we think of it like as x and y, like just domain and range, like the definition we learned?
Yeah.
Yeah, like so when it's saying the domain is bounded, so just think of it as x bounded, and then when it's saying the function is bounded, we can just think as y bounded.
Yeah. So when they ask if f is bounded, you think of the inputs. Well, my goodness. Okay. I'm getting a lag on this whiteboard, so 1 second. Yeah, so we think from, algebra and one variable calculus, we think of x as representing the input and y as the output. So we say that x is like in the domain, and then y is in the range. Yeah, so we can just kind of generally use that. I mean, you don't have to use letters x and y, of course, but yeah, you can think of the range of the function as all possible outputs, all possible y values. Okay. All right. Are there any students from Dr. Klavchevich's class, Dr. K? Roberto, aren't you in Dr. K's class? Yeah. So let me ask people from Dr. M's class, do you have any questions from the homework or something I can answer? So, because I do want to address students during Dr. K's class as well. I didn't look at continuity yet, but okay. So does anybody from Dr. K's class have a question? Let me make you all participants, presenters. You can use your mics. Okay, well, so let's move. Let's move on. So what do you call a? So again, let's terminology. We looked at scalar fields. So that's when the output was a real number. Scalar fields assign a number to each point in Rn. So what do you call functions which, for each point in n-dimensional space, assign an n-dimensional vector? So functions from Rn, yes, vector field. And so what's the typical example people use of a vector field on a weather map? So this would be an example of a vector field, let's say on R2. Very good. Wind velocity, right? So on the weather map, you can imagine that for each point on the map, you see a little two-dimensional vector which points in the direction that the wind is blowing, and the length of the vector represents the strength of the wind. That's right. So here you might get, let's say, a function on R3. So you have three inputs. So, and then you have an output which has three components as well. So this is like a function which is a rule that for each point in space you assign a vector. Okay. So I'm going to address Roberto in a second. So what do you, just finally, just for completion's sake, what do you call the function from, I should say, a subset of R, like an interval? So just a number line into Rn. An example might be, it's not a scalar function because the output is not a number, it's not a scalar. So a scalar function would be one where for each point in space you assign a real number, but this is the other way. The domain is a subset of the real numbers, and the output is a vector value function. So it's not a scalar field. This is a scalar field. It's called a curve, right? Because you think of the domain, let's say, in terms of physics as representing like a time parameter, and then for each point in time, you assign a position in space. So you think of this as time, if you're doing a physics analogy, and you think of this as space. So this tells you your position in space at time t, if you'd like. So you think of it as a trajectory. So if you animate that as time moves, whatever, as time changes, you trace out a path in space or curve in space. So this is called a curve. Okay, so now let me maybe address some questions from Dr. K's class. So thank you, Roberta, for being patient. You asked, oh, I used your name. Oh well, I can edit that out. So sine, volume, and distance from point to subspace. Sorry, I had to look at the. Okay, so you also encountered this in Dr. M's class. So sine volume from a point to a subspace. Sine volume. So I think of sine volume as of a simplex, but let's look at just a. So this is distance Yes, Colin?
My understanding is there are two different questions, question 1 and question 2 on Dr. Vishwa's homework.
Question 2 was...
So question 2 is the distance from the point to the subspace, and question 1 is signed volume of n-dimensional simplex.
Yeah, okay. So let's first look at just the distance between a point and a hyperplane, because you haven't really defined projections onto subspaces yet, have you? Okay. So let's do this. So imagine you have a hyperplane. In Rn, right? So what is that defined as? Well, if you take a single vector and make it non-zero in Rn, I'm using n because the typical language is that it's a normal vector to a plane, hyperplane. And you then say define the plane, let's call it V, as the set of all points in Rn, such that that set of points is perpendicular. So, and to set all x's that are perpendicular to this one vector. So in terms of dot product, that means the dot product is 0. You can imagine that we have all such vectors, drawing them from the origin, are perpendicular, so you get a plane. And in higher dimensions, that's a hyperplane. So you can define the distance between a point in space and this hyperplane. So imagine you have a point P. Let's use B instead, because P might, maybe I want to reserve that for projection. So let's use B. And you want to define the distance between this point and this hyperplane. Okay. So it would be natural, not natural, but it's the perpendicular distance, the shortest distance, right? I mean, so you can take, there are many distances from point B to points in the plane, but we want the shortest distance, so the perpendicular distance, so orthogonal distance. So we can think of this in terms of projection of one vector onto another. Okay, so we can think of projecting vector B onto this normal vector. And then the magnitude of that vector is exactly the distance we're looking for, right? So what you can do is say, okay, so the distance between point B and this hyperplane is exactly the magnitude of the projection of the vector onto the vector that's perpendicular to the plane. So that's going to be or if you'd like, the geometry of it. You want to project vector B onto this normal. You can so you want to find the length of this side of a right triangle. And so if you have this right triangle, let's say the angle between position vector B and normal vector is theta. And the hypotenuse represents the length of vector B. Okay, so I'm getting lost now. So cosine of theta is this adjacent side relative to our angle divided by magnitude of B, the length of the hypotenuse. So this length would just be magnitude of B times cosine of theta. And now suppose we multiply this by a unit vector pointing in the direction of n. And then you might recognize this from the formula, the magnitude of the product of the magnitudes of two vectors times cosine of the angle between them is exactly defined to be the dot product. Okay. So here we would have this expression is n dot, or n divided by its length, so that's that you're projecting onto the unit vector dot v is the adjacent side. Except I cheated, I drew the angle to be less than 90 degrees. Really, we're looking for a length, so you just take the magnitude. Okay. All right, so if your hyperplane is defined by all points perpendicular to n, where n has coordinates n1 through, wow, that's bad notation, nk. Okay, let me use better. Let's just say a1, a2, all the way through an, and your point has coordinates b1 through bn. We intuited geometrically that the distance between B and the hyperplane would be this simple scalar projection formula. Right, so I mean, I don't know what else to write. It's just, it is what it is. Okay. All right. All right, later, Colin. Thanks. All right. And so this is distance between a point and a hyperplane. There's a more general way of defining a distance between a point and a subspace. So, but I don't think, Robert, you can tell me whether you talked about projections onto subspaces or not. I didn't see that in the homework, so I was going to ignore it. Okay. So for the, did you want to go over the simplex stuff? So, so first of all, what is a simplex? Like a K-simplex? So let's look at a one simplex. So it's a simplex defined by one vector, and it would be the set of all points, which are, well, I won't use it. It's just all scaled versions of the vector v, where the scalar is between 0 and 1. Okay. So it's all, let's call it alpha times v1, where alpha is a number between 0 and 1. So if you look at V1, it's just a line segment essentially, right? All multiples of V1 would just be a line segment. And then the sine volume, or in this case, would just be of the simplex would just be the length of that vector. It's the length of the segment. Okay. So that's kind of not really informative because it's so trivial, but what about a 2 simplex? So you have 2 vectors. Yes, it's the area of the triangle that's defined between the vertices 0, 0, 0, and the positions given by vectors v1, v2. Right. Okay. So we would write the 2 simplex formally as the collection of all combinations of v1 and v2, linear combinations. So these are the scalars in the linear combination. But we want to make sure that all the combinations result in position vectors that remain inside this triangle, right? So that way we can just say that simplex is this triangle. So first of all, we're going to insist that the coefficients, or scalars in our combinations, are positive. So, so we don't want to have anything that's in the opposite direction of v1 and v2. But also to make sure that we stay in this triangle, we're going to insist that the sum of alpha 1, alpha 2, if the sum were equal to 1, so this is not correct, then all our vectors would end up somewhere over here on the boundary of this triangle. Okay. So if you want just the region, the triangular region, we're going to insist that the sum is 1 or less, at most 1. Okay. And so the sine volume of this simplex, I don't know how to denote this correctly, is just the area of this triangle. So it's going to be 1/2, let's say, base length let's say v1 is the magnitude of v1, and then the height. So notice that's the distance from v1 to the subspace spanned by so the distance between v2 and the span of v1. So that relates back to the idea of the distance between a point and a subspace. So that's the area of a triangle. And in the right, so what is a three simplex? What do you call that? So if one simplex is just a segment, 2 simplex is a triangle. What did you call it? Oh, it's 3 simplex. So we have to imagine we have 3 vectors. So it's like what do you call that 3-dimensional analog of a triangle, right? I think I can use blue. Yeah. It's a tetrahedron, right, in 3 dimensions. So you imagine that these three vectors drawn from the origin my whiteboard's getting really laggy for some reason. Okay, thank you. All right, so these three vectors are edges of a pyramid, if you will, with a triangular base. So a tetrahedron. Yeah, I'm sorry, but this whiteboard is really, really not acting correctly. All right, so tetrahedron. Okay, so the idea is that the volume, we would say, well, we know that the base here is a triangle, so you can say that it's the volume of a two simplex, right? So the triangle is a two simplex. And then we can multiply by the distance between the third vector w and that two simplex, or if you'd like, the subspace spanned by u and v. So you can say that, first of all, the notation for the three simplex would be the set of all points, which are the result of a combination of the three vectors where, to make sure we're well, we're going to say these coefficients are not negative, and that their sum is less than or equal to 1. So that's the definition of the three simplex defined by those three vectors. And you would say that the Sine volume of this three simplex, inductively you would say, okay, well, it's going to be the Sine volume of the simplex defined by the first two vectors, u and v. So that corresponds to the volume of that. You have to the area of this base triangle, and then you're going to multiply that by the distance between w and the subspace, which is the span of the first two vectors, and then you divide this by n, or 3. Okay. So you can see the general idea here. You have n vectors, which are independent, by the way. Well, let's just say they're independent, linearly independent. And so the n simplex, you would have to practice writing as it's all combinations of these vectors, these n vectors, such that all the coefficients are and the combinations are not negative, and their sum is less than or equal to 1. So this gives you like a generalization of an, if you'd like, an n simplex is like an n triangle, right? Even though that might be abusive notation since triangle implies 3, but you get the idea. All right, and inductively we define I guess the Sine volume here as being 1 over n, part of the definition, times the Sine volume of the first n minus 1, the n minus 1 simplex defined with first n minus 1 vectors times the distance between the last vector and the span of the first. So this gives us a very formal way of. Okay. So in particular, if you look at the simplex defined, sorry, it's almost time to go, but the simplex defined by E1, obviously that's just a unit vector. Okay, it's assigned volume would just be 1. Okay, so what about the assigned volume of the simplex defined by E1 and E2? Well, that would be the area of this right triangle. E1 and E2 are known to be perpendicular, correct? Like, you know what, the elementary columns. Oops. So these are perpendicular. So this would be, because this is 2, you go 1 over 2 times the, and what's the distance between E2 and the line, the span of vector E1? So the line through E1, it's just 1. And then times 1. Okay. Okay, so if you look at the 3-dimensional version, you have E1, E2, E3. So you want to compute the assigned volume of the 3 simplex, where you created was this ordered list of vectors. So that tetrahedron. So inductively, because you have 3 simplex, you'd say 1 over 3 times, yeah, okay. That's really acting up now. Okay, get rid of it, thank you. All right, so you would say that it's the assigned volume of the 2 simplex. So that's the corresponds to the base area of this triangle times the distance between E3 and the span of the first 2 vectors, E1 and E2. So that's pretty easy to see that here the height, the distance from E3 to the span of the E1 and E2 is just 1 again, because these are unit vectors. And we have nice J face. Yeah, you can. So I'm defining it in terms of just the distance between this last vector and the span of the previous 2. But you can define it for like an arbitrary vector in there, like Vj, the distance between Vj and the jth face. But this is 1/3 times 1/2, and this distance is equal to 1. Okay. So, and just a quick, like a pop. So it happens that for 3 simplex in R3, this would just be the determinant of the 3 vectors. A determinant of a matrix whose columns are the 3 vectors written in the ordered in the way that they were presented. So this is just divided by, in this case, 6, right? So in general, if you're elementary columns are ordered E1, E2, E3 through En. This volume would be, if you do the induction, would be 1 over n times n minus 1 times n minus, so that's n factorial times the determinant of the matrix you get if you stick your ordered list into columns of this matrix. And so we know that this is equal to 1. So one of the this kind of elementary simplex has a volume of 1 over n factorial, n-dimensional volume.
Wait, that is to find the simplex, correct?
Can you repeat the question?
But that is to find the simplex, right? Not the volume. The one
Well,
over.
so I was referring to really Dr. K's homework problem to address some of the questions there, where they were deriving. So in the Lax and Terrell book, they tell you this formula, right? It's a consequence. If you have a simplex defined by the elementary vectors written in the kind of conventional order, then this is the volume of that simplex. Okay. In Dr. K's class, they had a homework problem where they have to derive this. So I was trying to help them out. But in general, if you have a simplex defined by the origin and some number of vectors, and these are vectors in Rn, so all these vectors are in Rn. So this is a n simplex in Rn. Turns out that this is 1 over n factorial times the determinant of the matrix you get if you stick your vectors into columns of a matrix in the exact order. So it's fine because we know that if, so if you define a simplex in R2 using, say, vectors E2 and E1, that volume it's a signed volume because the determinant would be negative. You have to consider the order. So you have E2 first and then E1. There's E2, the second column is the E1. So we know this determinant is negative. So it's the area of the triangle signed. It's negative 1/2. And because I guess we need to, Levi, do you have a review at 12:30?
No, I'm in this class.
Oh, beautiful. Which, Dr. K or Dr. M?
Dr. M.
M, okay. All right, so I mean, it's over, but if you have questions, I'm happy to answer questions. I know some of you have like a quiz or something in Dr. McCohen's class. Okay. And Roberto, if you have questions about Dr. K's homework, I can answer those in a roundabout way. All right. Cool. So unless you have questions, that's it. Continuity. Right, very good. So I'll see Roberto, I'll see you in the drop-in lab. All right, so continuity. It's defined at a point. So do you remember the definition of continuity? Right, so we have an f, a function that's defined on some subset of Rn, and whose codomain is Rm. Okay, we say f is continuous at a point in the domain if what is true? If so given any epsilon, there exists a delta, so such that, and so epsilon and delta are positive quantity because they represent distances. So if we have that a point x is close enough, and x is of course in the domain, so if the distance, so you have to think of this as a distance between point x and point A is small enough, then we know that the distance between the value of the function at x and the function at A is small enough. So that's the distance between the function at x and the function at A is small enough. It's epsilon. Yeah, x has to be in D. I kind of have to mention that, but so all x in the domain, obviously. So that was a definition. I guess, what are some consequences? Well, I guess extreme value theorem is a consequence. So what did the extreme value theorem say, Adiat?
Oh, like if the function is like continuous
On what?
on a given interval, like from A to B,
But try to generalize that to
closed interval.
functions on some domain. So not an interval, right? But rather a subset of Rn.
If it in the set, if f is continuous in the set of D,
Mhm.
in D or something,
And what has to be true about the set?
it has to be closed,
And
bounded. No, right?
yeah, that's right.
Yeah,
So
it has to be
yeah,
closed.
so
Bounded. It's kind of
we
like
have
the
to have
interval has to be closed and bounded. Right. It makes sense. Yeah, it makes sense. Just
right.
kind of
So
like
it's not good enough to have continuity. We have to have continuity on a set which is closed and bounded. So the set has to contain its boundary points. I think in your homework they used the example of a unit cube a lot.
unit cube. Yeah. Yes. Or unit ball. Yeah.
So they had a set of all points.
1, 1, 1. Mm-hmm. Oh, and the maximum and minimum.
Yeah. So they used they described it as all set of points where x is between 0 and 1, y is between 0 and 1.
Right, and then z is also between 0 and 1.
And notice that it's an inequality that includes the possibility of equality because we have to contain the boundary of that cube. We have to contain the faces and the edges.
That's why it has to be closed and bound.
That's
Okay.
right. So that guarantees that it's closed. It's bounded because it's a finite volume, right?
Mm-hmm.
So what happens if f is continuous in a closed and bounded set?
Like there will exist like a global maximum and a global minimum.
Yeah, on that set, right?
Yeah, on the given set, right?
F attains an absolute max or global absolute
Yeah, absolute max.
max and minimum value on this closed and bounded region. So you can also use, instead of absolute, as you said, global is another way of saying it. Except it's
right.
global because it's just it happens on it's global
Because,
to,
I mean,
to the cube, right? So I don't know.
right. Like if there's only one maximum point in the whole set, so by default that is the absolute max because that's the only max.
Yeah. And so, is it possible that the maximum happens? Does the maximum have to happen at exactly one point, or can it happen at multiple points?
No, there can be multiple local maximums.
Yeah, and minimums as well.
Same for minimum.
Okay. And if they say that, let's give you an example. Do you have a quiz coming up?
Yeah, we're actually studying for that. Like this review is really helping for that.
So if we have that a function is continuous everywhere,
It's continuous everywhere.
it doesn't matter, it's continuous at a point.
Mm-hmm.
And they say that f of 1, 2, 3 equals 7.
Or is it the IVT thing?
What does continuity tell you?
Like, is it the IVT, like intermediate value theorem? Are you referring to?
No, it tells you many things, but
Like it has to.
Continuity says that if you're close to the point 1, 2, 3 in the domain, right? So if the point xyz is close, whatever that might mean, then if you evaluate your function at that point, then the value has to be close to 7, right?
What do you mean by
And
close? Like near? Like is near?
near.
Okay.
Yeah, close to.
Okay,
Near,
close
yeah.
to. Okay.
So you had questions like, so what does it mean for a point to be close to 1, 2, 3? It means, let's say, the distance squared. So the distance between these 2 points, point 1, point 2, is just the generalization of the Pythagorean theorem.
Like magnitude.
You take the difference in the 2 points and find the magnitude of that. So this distance, if it's less than some prescribed amount, then it's guaranteed that the value of the function, the distance between the value of the function and 7 is small, it's close, it's epsilon close.
Mm-hmm.
So this means that if you unfold this, and you add 7, right? The function evaluated at this point x, y, z, which is close to,
Like that's what it's bounded by.
yeah, then the value of the function will be guaranteed to be between 7 minus some small amount and 7 plus some amount. Okay, so is it true that if x, y, z is close enough to 1, 2, 3, I can guarantee the value of the function is less than 7.1.
That is
Yeah.
true. That is true.
Your epsilon would be 0.1, right?
Mm-hmm. And then
in fact, you could say that we can guarantee if we choose point x, y, z to be close enough to 1, 2, 3, then we can say that the function's value will be somewhere between 6.9 and 7.1. So this would be true, right? But if they say that if
because the point 1, 2, 3 equals to 7 exists.
Yeah,
Which is the point
exactly.
in between that.
Yeah, That's why we use 7 here, because that's what the value of the function at 1, 2, 3 was stated to be.
Right.
But if our point is, I don't know what's going on. When this whiteboard, when it's used too long, it just acts all funky. So anyway, I don't know. Oh, jeez, it's just laggy. So, but you couldn't say that the function would be bigger than 7.1, right?
No.
That would be false. So if
No.
your point is close enough to 1, 2, 3, then we can't. We can guarantee that the function is close to 7, but we can't. So we can guarantee that the function is between like 7 minus some small amount and 7 plus some small amount, right? But we can't guarantee that it's bigger than 7.1, only that it's less than 7.1.
Right.
That makes sense. So this would be false. Anyway, I gotta go to the lab, I guess. So
Yeah. No, this is good. Yeah.
later.
Thank you. Bye.
Thanks for joining me.